Okay, and today we're going to look at the fundamental theorem of calculus. But before doing so, we're going to review some derivative topics. Okay, I got you. So the first thing we're going to do is we're going to review the chain rule for derivatives. And the reason why we're revisiting this chain rule for derivatives is that when we use the fundamental theorem of calculus, you're going to see this derivative concept popped up. So just as a review, the chain rule is the outside inside derivative. So if you're dealing with a composition of functions, you would take the derivative for the outermost function, you will multiply that by the derivative for the innermost function, and that in turn would give you the derivative for your function. So here's an example. We have that y is equal to the sine of x squared plus x. And we're asked to find y prime. Right? And we're going to use the chain rule because this is a composition of functions. We have an outermost function. So if I cover up the innermost parentheses, our outermost function is sine. And we also have an innermost function. So if I cover up my outermost function, my innermost function is a quadratic, x squared plus x. So in finding y prime, can you hear now? If you can't hear, you may want to refresh your screen. All right, so if I want to find y prime, I'm going to take the derivative for both sides of my equation. So the derivative for y is y prime. If I take the derivative for sine of x squared plus x, I'm going to take my outside derivative. Right, so if I look at my outermost term, it's a sine function. The derivative for sine is cosine. So I'm going to write out my outside derivative as the cosine of x squared plus x. So notice when you use the chain rule in finding the outside derivative, the innermost function stays the same. Right? You basically take the derivative for the outermost function. So this is the outside derivative times the inside derivative. So if I look at my innermost function, which is x squared plus x, the derivative will give me 2x plus 1. So my derivative is the cosine of x squared plus x times 2x plus 1. All right, so just in a nutshell, that is the chain rule. It's the outside inside derivative. All right, so the next thing we'll do is we'll take a look at some notation facts, or some notations and facts. That's notations and facts. So when we talk about the integral for f of x dx, right, we talked about this notation, this S-shaped symbol, that's the integral. Every integral must carry a variable of integration. And remember that f of x is a function. The integral of f of x dx is equal to capital F of x. In our notations, wherever you see the capital F of x, that denotes a function that has already been integrated. So when we work out the fundamental theorem of calculus, the second part, well, the first and the second part, you're going to see this capital F. The capital F refers to an integrated function. So that's just as far as notation. Both of these things mean the integral, or an integrated function. Now, as far as the facts are concerned, differentiation and integration are reverse processes of each other. So that means that one will undo the other. For example, if you were to take the derivative for an integrated function, that would give you the function. And vice versa, if you were to take an integrated function, and if you were to find the derivative, it would return your function. So you're sort of undoing things here. The derivative and the integral are reverse processes. This is the same as the derivative with respect to x for f of x dx. Notice that these two things are exactly the same. They're integrated functions. These two are exactly the same. They are differentiated functions. So if you take the derivative of an integral, you get your function. Right, so I just want to point out the notation here that this capital F alludes to a function that has been integrated. So now we're going to look at the fundamental theorem of calculus, and it is actually in two parts. There is a part 1 and there is a part 2. All right, so I'm in the OpenStax Calculus 2 e-textbook, and this is on page 51. Right, the total page is 51, but it's 38 in the text. And this is the fundamental theorem of calculus part 1. And it says that if f of x is continuous over an interval from A to B, and the function capital F of X. So keep in mind this is an integrated function, is defined by capital F of X is equal to the integral from A to X of F of T dt. So notice that I have a function which is in the variable t. However, I have limits that are in the variable x. But notice these two things are equal. Then it says that f prime of x, capital F prime of x. So notice that this capital F is an integrated function. Prime means a derivative. So we're taking a derivative of an integrated function, and that returns the function f of x over the interval from A to B. Now we're going to get back to the first part of this theorem momentarily. However, I want to turn to page, I think it's 53. All right, and here is the fundamental theorem of calculus part 2. And for the fundamental theorem of calculus part 2, we are evaluating a function or integrating a function that has an upper and a lower limit. So this says if f is a continuous over the interval from A to B, and capital F of x is any antiderivative of f of x, then we have the integral from A to B for f of x dx is equal to capital F of B. So we take the integrated function and we evaluate it at our upper limit b minus the evaluated function, minus the integrated function evaluated at our lower limit a. So let's see how this works. All right, so the fundamental theorem of calculus part 2 says that the integral from A to B for f of x dx, that's equal to the integrated function evaluated at B minus the integrated function evaluated at A. All right, so here's an example. We're going to integrate from 2 to 3 4 minus 2x to the 3/2 power dx. All right, so the first thing we're going to do is we're going to integrate this function 4 minus 2x raised to the 3/2. And we're going to use a couple of formulas from our formula sheet. Okay, the formulas I'm using here are, the first formula says the integral of du is equal to u plus c. I'm also going to use formula number 4, which is the power rule, u to the power of n du, that's equal to u to the n plus 1 divided by n plus 1 plus c. All right, so I'm using these first couple of formulas, this constant formula and the power formula. All right, so if I integrate 4, I'm going to have 4x, right? So the constant rule basically says that I take my constant, I basically add my variable of integration, which is x, minus 2 times x raised to the 3/2 power. So I'm actually going to take this minus 2, I'm going to pull that in front of the integral operator. And I'm actually going to integrate x to the 3/2 power by using that power rule. So the power rule says that if I have x to the 3/2 power, I'm going to add 1. So that's my plus 1, but the 1 that I'm using here is a 2/2 type 1, which will allow me to add my fractions. Divided by n plus 1. And notice my limits are from 2 to 3. So if I were to simplify, I'm going to have 4x minus, and I'm going to write this all as one fraction now, 2x to the 5/2 power, right? Because 3/2 plus 2/2 is 5/2, divided by 5/2. Now, we're just simplifying this up a little bit. 5/2 in the denominator is 2/5 in the numerator. So what that means is I can actually write 2 divided by 5/2. I'm going to write this out as 4x minus 4x to the 5/2 power divided by 5, and our limits are still from 2 to 3. Right, so in essence what I did was I multiplied the very top and the very bottom. 2 times 2 is 4, and I placed 4 in the numerator. X to the 5/2 power remains in the numerator, and my 5 stays in the denominator. Right, so I simply reciprocated 2/5. I simply reciprocated 5/2 and multiplied by 2/5. Now here's where the fundamental theorem of calculus comes in. This is our lower limit A, this is our upper limit B, this is our integrated function capital F of X. So I'm going to take our integrated function, I'm going to evaluate it at the upper limit, so wherever I see an X, I'm going to substitute with 3. I'm also going to take the integrated function, evaluate it at 2, and we're going to subtract the 2 values. So now it should look something like this. I'm going to evaluate my integrated function at 3. So I have 4 times x, but I'm going to substitute x for 3, minus 4 times x to the 5/2, but again, I'm going to substitute x for 3, divided by 5. This is f of b minus f of a. Recall that a is 2, so I'm going to take the integrated function and we're going to evaluate it at 2. So I believe when all the dust settles on this for this first term, I got negative 0.47076 minus, for the second term, I calculated and I got 3.4741. And when I subtracted the two totals, I got negative 3.9453. So I'll give you a second to verify that. And we're going to take a look at another way to answer the problem. Okay, now for some of these calculations, we can use the calculator to kind of get this result. However, in other problems, sometimes we're just asked to integrate. All right, so if I were just asked to integrate, this would be my integrated answer, or my integrated function, 4x minus 4x minus 4x raised to the 5/2 power divided by 5. That's the integral. When I evaluate this integral at those limits, okay, this is my value. Okay. Now let's take a look to see how we can do this problem on the calculator. All right, so I have up my calculator, and in order to integrate using the calculator, I want to hit math. Okay, now these steps will apply for the TI-84, 84 plus, 83, 83 plus. I'm going to scroll down to FNINT, which is short for function integration, and I want to press enter. When you use the function integration function on your calculator, you must give it 4 parameters. You must put in your function, you must put in your variable of integration, you must then put in your lower and your upper limit. So I'm going to put in our function, and our function was 4x minus, I'm sorry, I'm looking at the integrated function. Our function was 4 minus 2x raised to the 3/2 power. Now, since my power is a fraction, I'm going to put 3/2 in a set of parentheses. Next, I'm going to insert a comma, which is above the 7 on my calculator. I have to put in a variable of integration, which is x. I have to put in my lower limit, and I have to put in my upper limit. Once I press enter, okay, notice it calculates the integral. What the calculator will not do, however, is it will not simply integrate a function. It can only integrate a function if you're given an upper limit and a lower limit. All right, so any questions about the first example? All right, now for the second example, before we talk about the fundamental theorem of calculus part 2, the fundamental theorem of calculus part 1. Okay, I'm looking at my notes. Okay, we already covered the notations and the facts that the derivative undoes the integration and vice versa. So now we'll take a look at the first part of the fundamental theorem of calculus. I believe that was on page 51. All right, so notice it says that capital F of x, which is the integrated function, that's equal to the integral from a to x for f of t dt. Then it follows that capital F prime of x is equal to f of x. All right, so now how does this work in practice? Okay, you may have seen some problems that look like this. These problems, I believe, were in section 1.3. F of x is equal to the integral from 4 to x for the function t to the 4th dt. Okay, this is what we're given. What we're asked to find is f prime of x. Right. So in this instance, we're going to use that fundamental theorem of calculus part 1. All right, so remember those facts we talked about a little earlier. Let me see if I can actually find those. We talked about the chain rule, right? The outside-inside derivative. And we also talked about the fact that when you take the derivative of an integral, you get your function, and then vice versa. We just saw that capital F prime of x is equal to f of x as well. So that's sort of the integration undoing a derivative, and this is sort of the derivative undoing the integration, but notice in both instances we yield the function. All right, so this is what I'm given, f of x. I'm asked to find f prime of x. So here is the process. In order to find f prime of x, I'm going to take the derivative, right? Because the derivative of f of x is f prime of x. Whatever I do to one side of my equation, I must do the exact same thing to the other side. So I'm going to take the derivative for both sides. If I take the derivative for my left-hand side, the derivative of f of x is f prime of x. So I've taken the derivative for the left-hand side. Now I'm going to take the derivative with respect to x for the right-hand side. So I'm simply going to write it out as d dx, right? The derivative with respect to x for the integral from 4 to x for t to the 4th dt. So the only thing I did here was I took the derivative for both sides. From my right-hand side, notice that I'm given my integral and I'm given my function. The function is in terms of t. So I'm going to pull out this fact. I know that f of t should equal to t to the 4th power. I'm going to put that in a box. I'm going to make a substitution, right? I'm going to substitute the integral from 4 to x the integral from 4 to x for t to the 4th dt as f of t, right, evaluated from 4 to x. All right, so what have I done? I mainly substituted. I substituted this integral symbol for the capital F. So this capital F of t is the integrated function. And my limits are from 4 to x. So I'm going to use the fundamental theorem of calculus part 2. So f prime of x is equal to f of x minus f of 4. Right, because wherever I see a t, I put an x, and wherever I see a t, I put a 4. Now I am going to distribute the derivative. So f prime of x is equal to the derivative with respect to x for f of x minus the derivative with respect to x for f of 4 and here's what happens. Notice that the derivative of an integrated function should give me f of x. When you evaluate an integral at some number, this is actually a constant value. If you were to take the derivative of any constant, the derivative of any constant is 0. So I have that f prime of x is equal to f of x, right? Well, how do I actually find f of x? I want to back substitute. To find f of x, I'm going to go back to my f of t function, and wherever I see a t, I'm going to replace it with x. So if f of t is equal to t to the 4th, f of x would equal to x to the 4th. So f prime of x is equal to x to the 4th power. So just to review this, this is what I was given, and this is what I'm asked to find. So I took what I was given, and I took the derivative for both sides of the equation, right? The properties of equality state whatever you do to one side, you do the same thing to the other. So I took the derivative with respect to x for both sides. Then I simply made a substitution. I substituted the integral symbol for the capital F. I still have my limits, right? These two quantities are exactly the same, they're just written in a different form. Then I use the fundamental theorem of calculus part 2. Right? I evaluated the integrated function at the upper limit minus the integrated function at the lower limit. Then we distributed the derivative. So when you take the derivative of an integrated function, it gives you back your integrated function. When you take the derivative of a constant, we get 0. And then lastly, we had to back substitute, right? In order to find f of x, okay, I went back to my f of t function, and I simply substituted x for t to get x to the fourth. All right, and I want to do one more. F of x is equal to the integral from 1 to x cubed for t to the third power dt. And here again, we're asked to find f prime of x. So this is what we're given, and this is what we're asked to find. All right, so we're going to go through the exact same procedure. Right? In order to find f prime of x, I'm simply going to take the derivative with respect to x for both sides. Right? And the reason why I'm taking the derivative with respect to x is because I'm finding f prime of x. So if I take the derivative with respect to x for the left-hand side, we have f prime of x. I'm going to take the derivative with respect to x for the right-hand side, so I'm simply going to write that as d dx for the integral from 1 to x cubed t cubed dt. So just as in the last problem, I have my integral and I have the limits on that on my integral. I also have my function, and my function has the variable t, right? So I'm going to write f of t as t cubed. Right? So here is the function of my integral, right? T cubed. All right, so next I'm going to just rewrite this integral using capital F notation. So f prime of x is equal to the derivative with respect to x for capital F of t evaluated from 1 to x cubed. All right, so keep in mind that this quantity in the brackets is the same as this quantity that's inside the brackets. We just written it differently by notation only, but they're exactly the same. Okay, so now in simplifying this further, I'm going to use the fundamental theorem of calculus part 2. We're going to take the integrated function evaluated at the upper limit minus the integrated function evaluated at the lower limit. So f prime of x is equal to d dx for f of x to the third minus f of 1. Right, so we're using fundamental theorem of calculus part 2. Next, I'm going to distribute the derivative operator. So f prime of x is equal to d dx for f, capital F of x cubed minus the derivative with respect to x for capital F of 1. So simplifying further, we're going to take the derivative for each term. So I'm going to bring down my f prime of x. So here, when we take the derivative, notice we have a composition of functions. We have an outermost function, which is f, capital F, I should say, and we have an innermost function, which is x cubed. So I'm going to use the chain rule here. So if I take the derivative of the outermost function, the derivative of an integrated function gives you my function, which is f of x cubed okay, this is the outside derivative times the inside derivative. Right, so the derivative for x cubed is 3x squared. This is the inside derivative. And then once again, the derivative of any constant is 0. All right, so in simplifying this further, how do we find f of x cubed? Well, I'm going to go back here. To find f of x cubed, I'm going to back substitute into my f of t equation. So wherever I see a t, I'm going to substitute with x to the third. So I have t, and I'm going to substitute t with x to the third raised to the third power, which gives me x to the 9th. Right. So if I substitute that in, we have f prime of x is equal to f of x cubed, which is x to the 9th, times 3x squared. And if I multiply these two things together, I have a final result of f prime of x as 3x to the 11th power. All right, so any questions about this example? All right, and I'll work out one last example. Okay, for one thing, the videos for these problems, they were not very clear on how to work these things out. All right, so here is our last problem. We're given f of x is the integral from 5x to 6x for z squared divided by z squared plus 15 dz. All right, so we're going to go through that same process. All right, we're asked to find f prime of x. All right, so I'm going to take the derivative with respect to x on both sides. So on the left-hand side, I have f prime of x. On the right-hand side, we're going to take the derivative with respect to x. Right, so we have the derivative with respect to x for the integral from 5x to 6x for the function z squared divided by z squared plus 15. So I have my integral, I have my limits, I have the function of my integral, right, which has a variable z. So I have f of z is equal to z squared divided by z squared plus 15. Right, this is the function of my integral. Okay, so next I'll replace this integral symbol with the capital F notation. So this simply becomes capital F of z from 5x to 6x I'll use the fundamental theorem of calculus. So that's capital F of 6x minus capital F of 5x Oh, I'm sorry, I already wrote that out. Okay. All right, so 5x. Okay, I substituted in b and a. All right, so the limit should actually disappear here. So now I'm going to distribute the derivative operator. So f prime of x is equal to the derivative with respect to x for capital F of 6x minus capital the derivative with respect to x for capital F of 5x and I must use the chain rule, right, for both of these terms. Right, so if I take the outside inside derivative, the derivative for capital F of 6x would be F of 6x. And if I take the derivative for my innermost term, I have 6 minus the derivative for my outermost term would be lowercase f of 5x times 5 So in order to find f of 6x and in order to find f of 5x, I would simply substitute those into my f of z function. So f of 6x would equal to 6x quantity squared divided by 6x quantity squared plus 15. F of 5x is going to be 5x quantity squared divided by 5x quantity squared plus 15. All right, so now if we put this all together, I believe you should have something that looks like this. So f prime of x is equal to 6 times 36x squared divided by 36x squared plus 15 minus 5 times 25x squared. You can't even see that. 25x squared divided by 25x squared plus 15. And then this will give you a final result. F prime of x is 216x squared over 36x squared plus 15 minus 125x squared over 25x squared plus 15. All right, so I'm going to go back to our, I guess, to the camera screen here. Okay, are there any questions about the fundamental theorem of calculus part 1 or part 2? Okay, now these what we actually went through today for section 1.3, there were the first few problems in that section that dealt with this fundamental theorem of calculus part 1. So based on all of the lectures up to this point, those 2 video lectures and also this lecture, I believe you should be able to answer just about anything in any one of the sections except for the very last one, I believe. When we meet again next week, we will finish the chapter 1 topics. I know there's some things I didn't touch on. I'll kind of touch on those things next week. I will review some of the substitution material because some of the substitution methods you go through with chapter or with the exponential function, they may require a little bit of explanation. So here I'm going to actually stop the recording.